Hi, this is going to be sections 910 and 911 for Chemistry 1151. So the last section of chapter 9 is going to be about buffers, and buffers are really important in real life, in the body. We're going to talk about a really important buffer in our blood, so we need to understand what a buffer is. A buffer is a solution whose pH changes very little if you add acid or base. So basically you can think about a buffer as like a way for the pH to stay relatively the same. It's like a defense system against additional acid or base being added. So most buffers are solutions composed of about equal amounts. Now that's equal molar amounts specifically. So you wouldn't just think about the grams of each of these substances, but we were thinking about the moles. So we can write equal molar amounts of a weak acid and its conjugate base, specifically the conjugate base that comes with that weak acid. And what is a salt? A salt is just an ionic compound. So it's an ionic compound that's made from an acid-base reaction. So the salt of its conjugate base would be the ionic compound containing the conjugate base. So as long as you have the conjugate base in there, that can be a part of a buffer. The buffer resists change in pH because if you add base, which is hydroxide, it reacts with the weak acid. If you add acid, it reacts with the conjugate base. So if we add base, the weak acid in the buffer goes to neutralize that base. If we add acid, the conjugate base in that buffer goes to neutralize the acid. So we have both, we're prepared for an attack of base because the acid is ready to go, or an attack of acid because the base is ready to go. So basically what you need to know about buffers as far as just bare minimum is this slide. This slide is giving you bare minimum of what you need to know, what a buffer does, what it's composed of, and a little bit of how it works. We're going to go deeper into how it works in just a minute. So here's a little bit about what a buffer does. So if we look at a buffer here, let's look at water. We have water has a pH of 7, which is neutral. If we add some HCl, which is acid, see how the pH drops to 1.7? That's a pretty big drop. Remember that every 1 drop of pH is 10 times more acidic or basic. So from 7 to 6 is 10 times more acidic. This is from 7 down to 1.7. So 7 almost down to 2. That's a lot of times 10s. Every time we go 7, 6, 5, 4, 3, 2, 1, that's 10 times every time we move down the pH scale. So this is way more acidic than neutral water. However, if we start with water and we add a base, we can think about what direction we're going to go. We went from 7 to 12.3 pH. So if we add even just a small amount, 0.02 moles, it's a pretty small amount of acid and base, the pH changes a whole lot. Now let's look at the buffer and compare. So if we start with a buffer, let's say the buffer starts at 4.76. If I add acid, it only goes to 4.72. It didn't even change a whole pH value. It just changed on the fraction. And it still changed though, so that's one thing to note is that the buffer pH still changes, but just a small amount. So we still have a lowering of the pH from 4.76 to 4.72, but it's just a very small amount. And then if we add a base, we're going to raise the pH up, but again, only by a small amount, so 4.76 to 4.79. So we see a big difference in pure water versus an actual buffer. So buffer is doing its job here. So how does the buffer work? So if we add an acid to a buffer system is actually an equilibrium because we have a weak acid. So this is my weak acid that's in the buffer. And we have its conjugate base. That's this one. And we have both of them present so that they can go back and forth. And so we have this back and forth arrow that allows the equilibrium to move around. If you add more acid we're adding hydronium. Remember, that's acid stuff. So if I add acid stuff to my buffer situation, if we add products, remember that add, we shift away. So as soon as we add it, it's going to shift to the left. Well, it can only shift to the left if we have conjugate base here to react with acid to then neutralize it. So we have to have this present to be able to shift to the left. So if we add more acid, for just a moment, there'll be too much hydronium, my pH would drop, but then I'm going to shift to the left to get rid of that extra acid stuff, and it will go back to around the same pH, but not, maybe not exactly the same, but definitely not as much as if it were water. And so because this is going down a little bit and this is going up a little bit, the ratio does not change very much. My acid-base ratio does not change very much. And so this does not change very much. And if this doesn't change very much, the pH doesn't change very much. So these things are all related. So hopefully you can recap your equilibrium and so you understand all those equilibrium changes, Le Chatelier's principle, and that stuff. What happens if we add a base? So if we add a base, remember we have our weak acid here, and we have our conjugate base. So this time we're going to look at the weak acid reacting with this base. The weak acid reacts with the base. We're going to decrease the amount of weak acid a little bit and increase the amount of conjugate base a little bit, but the ratio is going to be relatively the same. Now, if we add a whole lot of OH, that OH is going to be going to do something. So if we add OH to our situation, it's going to react with H3O plus, and it's going to make water. So what happens to my H3O plus when I add OH? The H3O plus concentration decreases because now you have this secondary reaction. So imagine this is happening where this is my acid, it's going back and forth. If all of a sudden I get rid of H3O plus because the OH is over here grabbing it, I'm going to have less H3O plus, which means my pH is going to go up. But my weak acid will neutralize this OH minus. So we'll shift away from what we just added, and that's going to stop the pH from increasing. So if we in this other situation here, if we just add OH minus without stopping it, but if we add it, we can actually use it up by our weak acid here reacting with it. So at the end of the day, the H3O is not going to change very much because my weak acid is neutralizing OH minus. So the H3O plus doesn't go and have to neutralize the OH minus. It's a little bit different. This is an oversimplified way of thinking about this, but I think this is enough just for you to get by with it. So common buffers would be acetic acid and acetate. Notice the acetate is the conjugate base of acetic acid. Bicarbonate and carbonate. Dihydrogen phosphate and hydrogen phosphate. And so these are all acid conjugate base pairs. And then we can see the Ka's here showing these are all weak acids. So the Ka is showing these are weak acids. So you have to have a weak acid because if you don't have a weak acid, then you can't go back and forth with your equilibrium. So it can't be a strong acid. So we come back up to the very beginning. Cannot be strong. If it's strong, it can't be a buffer because we don't have an equilibrium, and we got to have an equilibrium happening with both of these situations. So how do we calculate the pH of a buffer? You do not have to know this for lecture, but you will have to do this in lab. And so the effective range of a buffer. So some buffers are good at keeping pH at 4. Some buffers are good at keeping pH at 5. Some buffers are good at keeping pH of 7. We start out with our Ka expression of our acid, and then we wind up solving for H3O plus, and we get this formula here. And again, this is just showing you how it's derived, but the formula we're going to be using, I guess we'll talk about it later. So here, the hydronium ion concentration that then goes to determine the pH. Remember, the pH is equal to negative log of hydronium. So we have this is your acid, and this is your conjugate base. So your acid and your conjugate base are about the same. This would be 1. And so your amount of acid stuff would be about the same as your Ka. So the Ka is really what makes the buffer it figures out like what pH you want to work with. You don't need to know this in like super detail. We'll talk about another equation, but you'll definitely use this in the lab if you're taking a lab class. So how do buffers work in nature? One thing is that a lake surrounded by limestone, calcium carbonate, has a natural buffer in it. And so any sort of acid rain or acid precipitation contains nitric acid and sulfuric acid. If you have a lake that doesn't have any sort of limestone around it, it's not going to have a natural buffer, and it will decrease the pH of the lake when it rains. And then if it has a natural buffer of limestone, then you will not have the pH change very much. So it just kind of depends on what's around the lake, and lakes can be naturally buffered or not. The human body is probably more relevant to all of us. Neutral blood or normal blood pH is between 7.35 and 7.45. The principal buffer in the blood is carbonic acid. And so these little arrows are actually written incorrectly. So I'm going to change these. I might rewrite this whole thing for you at some point. But we go this way. This is actually adding water. It goes here. So we have a kind of a two-step buffer system. So the bicarbonic acid is our weak acid, and our conjugate base is bicarbonate. So the buffer here, we have to have about equal amounts of weak acid and conjugate base. So if we add a bunch of acid, that conjugate base comes in, and that reaction moves to the left to get rid of that. If we add a bunch of base, this will go down, and we're going to react with that OH minus to shift it to the right to increase our amount of H3O plus we make. And again, I'll talk about this a little bit more in class and help you with any questions that you have. But basically, when how do we make the carbonic acid? Well, we're constantly making CO2 in our body, right? And so CO2 dissolved in water to make that carbonic acid. So therefore, the amount of CO2 is related to the pH of the blood. So if you hold your breath, then you can change the pH of your blood by having too much CO2, or if you're hyperventilating, you can change the pH of your blood. So let's talk about that. Respiratory acidosis is when the body fails to eliminate CO2 and it increases your amount of acid stuff. So if you have a buildup, so we have increase of CO2, so we're going to add CO2. If we add CO2, we shift away from CO2. This makes more H3O plus, and so if you have more H3O plus, you're going to have a lower pH. We call this acidosis because we're more acidic. And it's respiratory acidosis because it comes from not eliminating carbon dioxide. So if you were to hold your breath, or if you have any sort of lung issues, then that can happen. Respiratory alkalosis is the opposite. So alkaline means basic. So if you ever see alkaline anything, this means basic. So alkalosis, like hyperventilating. So very little CO2 is getting produced. So we lower the amount of CO2. Our reaction is going to shift to the left because we're taking it away. That's going to decrease the amount of H3O plus and lead to a higher pH, which is more basic. There are other types of alkalosis and acidosis. You'll talk about that in your worksheet for this chapter. But that's it for the actual content. We'll do more practice in class.